Okay, so right now we're going to be drawing a force diagram for the water skier. This is going to be problem 1 on Unit 4, Worksheet 1, Part 2. Draw a force diagram for the water skier. Label the force vectors and use equality marks on the vectors. So that first step, which is to draw the situation, has already been done for us because this has been printed out. So now what we need to do is we need to identify the system boundary. So that way we know what we're drawing a force diagram for. We're drawing a force diagram here for the water skier. So I'm going to draw that dotted line, which represents our system boundary around the water skier. That object, everything inside that system boundary, is going to be the center of our force diagram. And that is going to be our water skier. Now that we've identified the system that we're looking at, identified the boundary across which forces are pushing or pulling on this skier, we can start to identify which forces we need to include on the force diagram. I recommend starting off with any non-contact forces. We have 3 types of non-contact forces: the force of gravity, the electric force, and the magnetic force. Now, we will almost always be putting a force of gravity acting on our object in a force diagram. So that's the first force I'm going to draw. The force of gravity would be pointing down. This is the force of gravity. So we identify the type. It is acting on the water skier, and it is caused by the pull of the earth. So that's the fully labeled non-contact force of gravity pulling down on our water skier. We have 2 other types, the electric and the magnetic forces. But those are not necessarily something that will be acting on this water skier right now, because we don't have any reason to believe that they would be. So we're not going to include that type of force on this force diagram. That just leaves our contact forces. So we need to see what is physically crossing the system boundary to see what could be exerting a force. The first thing that I see is crossing the system boundary is this rope. Now the rope can either be pushing on the water skier or pulling on it. I'm going to say that because this is a rope, it will probably be pulling on it. And that's also, seeing as I've been water skiing, I know that's what it does. The rope pulls on you, which is why you follow the boat that's pulling on you. So we have this force that's crossing the system boundary, and it is pulling on the water skier to the right. So I draw a force vector pointing to the right, and I'm going to label that F for force. The type of force that this would be associated with would be tension. It is acting on the skier, and that is caused by the rope. What else is going to be touching the water skier is going to be the skis, if we did not include that as part of our force diagram, or the water. Now, the person is not standing directly on the water, they're standing at this type of angle. So the water would either be pulling them down or pushing them up. Now, the water will probably be pushing them up because the person is floating on top of the water. So our force would kind of match this direction. Not directly up because they're not standing flat on the surface, but up and slightly to the left. So that's going to be a force. And then I'm going to say, because it's a floating force, I'm going to identify that as the buoyant force. This buoyant force is acting on the skier, and it is by the water. Now, the only other thing that I can see that is touching the water skier is going to be the air, which is surrounding them. Now, air is surrounding them all over the place, so we need to kind of make an assumption for why the air could be exerting a force if we want to include one. Now, we can say that this water skier is probably moving in this direction, because that's how the water skiing is going to be working. If they're moving really fast, they might feel the air hitting them and notice like a push backwards from the air itself. So we can say that the air could be exerting a force on the water skier to the left. It's trying to resist their passage through the air as more and more air particles hit them. This type of resistive force in the air is called drag. It is the force of drag on the skier by the air. Other than that, we don't have anything that is crossing that system boundary, so we don't have anything else that could be exerting a force on this water skier. So now we just need to identify what the sum of the forces is going to be, and identify any equivalencies that may exist. Previously, we were able to do that just by seeing what forces we have up and down, and what forces we have left and right. The problem is, if we were treating this like an XY graph, this buoyant force right here is not directly on the x-axis or directly on the y-axis. So we need to break that up into its components in order to see what would end up canceling out. In order to do that, we're going to break it up into its horizontal and vertical components. I'm going to start off by identifying the vertical components here. So I start off at the origin, and then I see how high up on the y-axis that buoyant force would go. I'm representing it with a dashed line to say that this is not the full-on force, it is just part of a force. And I'm going to label that as the force buoyant in the y direction, the up and down direction. I need to know how much over it's going to be. So I know that if I go tip to tip on these two force vectors, that is going to be the length between them. So that's how far to the left the force is going to be applied. But I don't want to necessarily include it up there, because that implies the force is not applied to the skier, but somewhere above them. So I'm going to once again start at the origin, and then draw a component force vector the same length as the one that completed that triangle up above, and label this. This is the buoyant forces horizontal component. So that way, I've now taken that original buoyant force, which is up and to the left, and figured out how much of it is associated upwards, that I have up there with that green force vector, and how much of it is to the left, that left force vector. Now I just need to write an equation in order to show what the sum of the forces is going to be. So if I break this down into its two parts, once again, I'm going to start off with the sum of the forces in the y direction. So this symbol that looks like an E is a Greek letter sigma. It's a mathematical symbol that means the sum of, and then the F is for the forces. So the sum of all of the forces in the y direction. I'm going to, well, combine all of those forces. We have a force buoyance in the y direction. It's not the full force, but just that vertical component. And we have the force of gravity in the downward direction. Now I haven't put any signs in front of them because this is going to be a good chance for us to identify whether they should be positive or negative forces. If we're treating this like an XY graph, with the skier being the origin or the point 0, 0, everything above our object would be a positive force. So that would make this buoyant force in the y direction positive. Everything below the skier, or everything with a force pointing downwards, would be negative. So we have a positive force and a negative force. We don't know what the quantities are here, but we can make an assumption about what these two combined would have as an effect on this object. This water skier should be floating on top of the water. They should not be launched up into the air. They should not sink into the water itself. Their motion vertically should remain unchanged. So if their motion is going to remain unchanged up and down, that means that the sum of their forces vertically should equal 0. This is one way to write it. Alternatively, we could rearrange that equation to show that the buoyant force in the y direction is equal in size to the force of gravity. Just rearranging it like we would a math equation. So we could say those forces are equivalent. This right here is going to be our sum of the equations vertically. We need to do the same thing for the sum of the forces horizontally. Now this is where we have three forces horizontally. We have a force of drag on the skier by the air. That is pointing to the left. So on a graph, we can say that that would be in the negative direction. We have a force buoyant in the x direction, which is also pointed to the left. So we can say that that is going to be negative. And we have a force of tension to the right, which we can assume is going to be positive. So these are going to be the three forces we have. Now we need to figure out if there's going to be a change in motion of this water skier. Well, this water skier, if their velocity is not constant, that means the forces would be unbalanced. So if their velocity were decreasing, they were slowing down. What that would mean is there would be more forces pointing to the left than there were to the right. But as long as this rope is completely stretched in, like completely tight, we know that it's going to keep pulling on them, and the only way that they would have more forces pointing backwards is if that force disappeared. So we can't have more forces to the left than we do to the right. Now what we could have is more forces to the right than we have to the left. What that would mean is that this person would be speeding up. However, if they were speeding up, that means that they would be getting closer and closer and closer to the boat that is pulling them, which would probably be a pretty dangerous activity for this person to get close to a moving boat. So in order to make the assumption that this person is going to be safely water skiing, we know that their velocity at this point should probably be 0 as the sum of all of their forces. This allows us to rearrange this equation then to say that the combined effects of the force of drag and the force buoyant in the x direction are equal in size to the force of tension. We have two forces to the left that have to be equal in magnitude to the one force to the right in order for us to have a sum total of the forces equal to 0 horizontally acting on this water skier.